Have you ever wondered if the silence of the universe is actually hiding a noisy conversation we simply haven't learned to hear? What if the very tools we built to listen to the cosmos are subtly distorting the message? Not because of faulty engineering, but because of the invisible wind blowing through space itself. Welcome to a journey through the latest breakthroughs that are reshaping our understanding of the universe. Today, we are diving into a convergence of discoveries from gravitational waves, dark matter, and the fundamental constants that hold reality together. We will explore how a hidden bias in our detectors challenges decades of assumptions, why the search for dark matter has narrowed to a specific, elusive range, and how the stability of the stars themselves confirms the reliability of the laws of physics. Stay until the end because the implications of these findings reach far beyond the laboratory, touching the very design of our future space missions and our quest to understand our place in the cosmos. For decades, the scientific community has operated under a comforting assumption that if a single detector has low internal noise, its measurements are unbiased. We believed that by isolating our instruments from earthly interference, we could achieve a clear view of the universe. Similarly, in the hunt for dark matter, researchers have cast a wide net, looking for particles across a vast spectrum of masses. In the realm of fundamental physics, there has been a lingering question whether the constants that govern atoms and light might shift over the eons of cosmic time. These separate inquiries seemed distinct, yet they shared a common thread: the struggle to distinguish true signals from the background hum of the universe. The problem was that we were looking at the pieces in isolation, potentially missing the larger picture of how environmental factors and cosmic history intertwine to shape our data. But now, a new paradigm is emerging. Recent analysis has revealed a startling truth about our gravitational wave observatories. It turns out that correlated noise from solar wind plasma creates a systematic bias in our measurements. Even when individual instruments appear quiet, the collective network is influenced by this environmental ripple. Imagine trying to hear a whisper in a room where the air itself is vibrating. No matter how good your ears are, the medium carries its own distortion. This study found that this correlation introduces a bias of over 12% in power law models and nearly 20% in cosmic string theories. It forces us to realize that low noise in one detector does not guarantee an unbiased result when multiple detectors work together. At the same time, the search for dark matter has undergone a dramatic refinement. By analyzing 13 years of data from cosmic ray interactions, scientists have effectively ruled out traditional models of dark matter, with masses below a few million electron volts. Think of it like searching for a needle in a haystack, only to discover that the needle isn't made of straw or wood, but of a specific, dense metal that only appears under very particular conditions. This discovery pushes the sensitivity down to the KHI scale, closing the door on many phenomenological models and narrowing the hunting ground for new physics to a much more specific, albeit challenging, territory. Perhaps most profoundly, high-resolution spectroscopy of hundreds of quasars has confirmed a remarkable stability in the fabric of reality. Over 4.5 billion years, the fine structure constant and the proton-to-electron mass ratio have remained statistically unchanged. This is akin looking at an ancient photograph and finding that the colors have not faded at all, proving that the rules governing atoms today are exactly the same as they were when the universe was young. This null result is not a failure. It is a powerful tool that tightens constraints on theories of varying constants, stabilizing the foundation upon which modern physics is built. This wave of insights extends further, revealing new methods to track the evolution of black hole binaries through luminosity deficits, and using spectropolarimetry to distinguish the composition of cosmic jets. We are even detecting planetary mass satellites around nearby brown dwarfs, overcoming previous limitations of stellar contamination. These advances show a clear shift toward multi-messenger methodologies. We are no just collecting isolated data points. We are weaving together solar wind dynamics, cosmic ray interactions, and gravitational signals into a unified tapestry. The field is moving away from confirmatory studies of single phenomena toward integrated frameworks that cross-correlate diverse data streams. The implications of this convergent shift are profound for science, technology, and humanity. For gravitational wave astronomy, Identifying this correlated solar wind noise means we must revise the sensitivity curves for next-generation networks like LISA and KHI. This directly impacts the design of future space-based interferometers, ensuring they are built to account for environmental correlations that were previously ignored. In particle physics, the tightening constraints on light-dark matter and fundamental constants provide a stable foundation for extending the Standard Model, guiding the priorities for massive experimental facilities. For engineers and instrument scientists, the validation of indirect tracers offers a practical revolution. Instead of relying on uncertain direct imaging or model-dependent fitting, we can now use robust empirical markers like luminosity deficits and Faraday rotation to monitor transient events and accretion geometries. This allows for cost-effective, data-driven diagnostics that can track the evolution of black hole binaries and cosmic jets with unprecedented clarity. It transforms abstract theoretical debates into actionable NG.